Okay, so yesterday we were actually discussing on maximum likelihood estimation. Okay, and we have seen we have to maybe find out the parameter vector theta, so which will actually maybe maximizes the likelihood that that particular theta actually generated the given data set d. So that is actually our aim. So we have seen that and so we have seen this particular case also, maybe a sample case where we have a various for a given data, what is theta gap and what is actually a log likelihood. Maybe representation, and maybe in that case also theta gap represents the best value. Okay, and now we will see how we can actually maybe analytically maybe find out maybe theta. So that means we are actually looking for some optimum estimation. So we assume that we have a theta, theta 1, theta 2, etc. to theta p. Okay, so that is actually the theta vector. Okay, and now in order to find out the optimal value, so we have to define the gradient operator, because so here how this is actually find out is we partially derivate the given maybe the probability value with respect to each of the parameters, that means theta 1, theta 2, theta v, and then from there we actually find out the best value for theta 1, the best value for theta 2, etc. Okay, so that is actually the procedure that is generally followed. So we actually use a del operator, which actually represents the partial derivative. Okay, so del theta means we are actually partially derivating a function with respect to theta. So here we define the operator, gradient operator, dou by dou theta 1, dou by theta 2, etc. to theta p. Okay, so depending upon how many parameters are there in the parameter vector theta. Okay, so that is the idea. So we'll come to that representation again. So that means we have also defined actually the log likelihood function. Okay, so assume that we represent that using L of theta. Okay, so that means L of theta is actually natural logarithm of say probability of d given theta. So that is because likelihood is actually probability of d given theta, and that is actually a function of maybe theta. So that's why we represent using L of theta. Okay, so log likelihood. So we know that d is actually the training data set that may be with respect to one category, or maybe whatever data that we are actually considering for finding out the best theta. So that is actually maybe the concept of log likelihood. So we just taking the logarithm of the likelihood function, that's all. Okay, anything additional in that particular say step. So we can say that the new problem statement is that means the new what we are actually trying to find out is we know that we have to determine the theta that maximizes maybe the log likelihood function. So earlier we have before introducing the log likelihood, it was actually maximizing the likelihood. Now it is maximizing the log likelihood. Okay, so that is again theta cap. Okay, which is you find out which theta that maximizes the log of the likelihood function. So that is actually the argument function. Okay, so argument max of theta, L of theta. So that means so this particular function will return the theta that maximizes L of theta. So you will try different and that is actually the theta cap that will be used for maybe for the further analysis. So that means using that theta cap only we will be finding out maybe the decision boundaries, that is the discriminant function values, and so okay, so that is the idea of maybe the best value. And now we will look into L of theta. Okay, so we know that so the theta is actually we have defined as a product of, okay, so that is we have actually defined it like this, in probability of d given theta we have defined as k is equal to 1 2 n. Okay, so considering the independent nature of each of the maybe say sample points. Okay, so we have considered this particular equation, so product. Okay, so we substitute that here. Okay, say log likelihood okay function, then that product will maybe change to a summation, okay, and we are actually taking the logarithm of probability of xk given theta. So I think that is easy to maybe understand, because we this is actually we have a probability of d given theta, okay, and we substitute that pi, okay, that pi, okay, probability of xk given theta, okay, and so that we will get this equation of this kind, okay. So that is because we are actually applying the logarithm, so that will convert it to an addition, okay. So that is why this equation we are having. And now from for this particular L of theta, okay, we can have actually maybe say what is actually the gradient of, okay, L, okay, say with respect to the theta. So that is nothing but we are actually applying the, okay, gradient here. So that is again k is equal to 1 to n, okay. So the gradient of this particular say function. So that is a way we can actually maybe define the gradient, okay. And so now how we will find out maybe the optimum value of theta, because okay, so that is maybe from the calculus, okay. So the equation is actually we maybe form an equation of this kind, okay. So that is del theta of L is equal to 0, okay, and then you solve it for, okay, theta 1, theta 2, theta 3, etc., okay. So that is actually the idea, how we can actually find out maybe the best theta. But usually when it comes to machine learning, we have a maybe, okay, analytically solving maybe when the theta increases, that is a parameters increases, okay, that can be complex task, okay. And also when the number of features increases, okay, so manually solving all this can lead to, okay, maybe very complex, okay. But there are some other alternatives that we will discuss later. Anyway, so this is actually the way how we can actually find out the best theta, maybe, okay, in this particular case, okay. So now we will, what we will do is we will go to some specific cases, okay, and see how we can actually whether this whatever we have discussed here, maybe in order to find out the best theta is really correct, okay. So the procedure that we have followed is really correct, whether so that means is there any point in, okay, taking probability of d given theta, okay, so that maximizes the theta is actually the best value, okay, whether so that whatever we followed is actually correct. So for that one, assume that we take a particular case where we have the Gaussian case, we assume that the probability density is actually Gaussian in nature, and for the time being, for maybe for a simple case, assume that the only unknown value is mu, and we know the covariance matrix. So that means because when you are having a normal distribution, okay, either a covariance matrix or a variance, okay, depending upon how many features are there. So we are assuming that the probability of xi given mu is, okay, approximated to the normal density of mu and sigma. So that is actually the idea. So here we have a theta is actually equal to mu only. Okay, we have only maybe only one parameter here, because the other one covariance we are assuming that that is known. Okay, so non-parameter we don't need to find out it again. So that means here theta vector will contain only the mu value. Okay, and we have already, okay, the assumption that it is a multivariate normal population. Okay, we are actually considering. So whatever the next discussion is, we are just substituting, okay, maybe, or we are just finding out the del operator, okay, whatever we have seen in the previous slides, okay, we apply for this normal distribution. So assume that we have a probability of xk given mu. So that means this is nothing but something like a probability of xk given d. Theta we have a c, okay, earlier. So here theta is mu. So that means, and we are actually considering the logarithm, okay, function. So that means here we have actually the previous equation, okay. So we know what is actually the the equation for Gaussian distribution, okay. We have a 1 by, okay, 2 pi raised to d by 2, okay. So that equation we have already studied, okay. sigma inverse then okay into e raised to minus. So that equation you know. So that we apply okay logarithm okay on that particular equation. So we will get an expression of this kind. Okay. So that is we apply some log a by b rules. Okay, then log a b is equal to log a plus log b. So if you apply all such maybe basic laws of logarithm, okay, on the maybe in the normal distribution, okay, equation that we had already discussed, we can obtain an equation of this kind. Okay, maybe you can just maybe apply and you can try your own maybe to see whether this is correctly getting. But as I mentioned, you just apply the basic laws of logarithms, okay, and rearrange the things, then you will reach this particular equation. And now what we have to do is we have to find out the del theta of L. Okay, so that was the one we have to see. So that means instead of we know that the theta it is mu, okay, and this is actually the logarithm. Okay, so that is ln of okay this particular value. Okay, and so that means you are actually what you are doing is actually with respect to mu you have to maybe partially derivative this equation. Okay, so if you look into this particular term, okay, this particular term there are no maybe the mean value comes in, so mu is actually not there. Okay, so that means maybe you can that will become zero, and here you have to apply okay maybe the partial derivative. Okay, so in that case you can say that some after some rearrangement, suppose this is you can put xk minus mu into xk minus mu, so that means you will get a xk minus mu okay the whole square of form. Okay, and sigma inverse is always there, so that is we kept as a multiplier, and then you apply okay the derivative on that xk minus mu the whole square, so that will return 2 into xk minus mu into, and as you have a minus mu here, you again partially derivative, so that means you'll get a minus 1. So that minus 1 and this minus 1 will become a plus 1, and you have a sigma inverse into xk minus b. So you can reach this equation. So that is just applying the partial derivative rules, okay, and maybe rearranging. So that means here we know that theta is mu, okay, and then what we have to do is we have seen an equation theta of L is equal to 0. So this is a way how we can actually find out the optimum value for theta. So that principle is actually applied here. So that means we have already found out what is delta, okay, mu of maybe this particular function, and then we equate that to 0. But before that, we know that so this is actually for the whole sample set. So that means okay, this is just for one sample we have seen here. Okay, so now k is equal to 1 to n sigma inverse into xk minus okay here we write a mu cap. So that means because whatever solution we are getting from this equation okay is actually the optimum value or the best value. So that best value we have already represented as theta cap, but here we have a mu cap, okay, because we have a theta is equal to mu. So that is the way how we can actually maybe write this equation. Okay, and then we can the previous equation, suppose we just multiply okay sigma on both sides, okay, so that you'll have a sigma into sigma inverse will be okay cancelling, and then the remaining thing okay it is going to be x1 minus mu cap okay plus x2 minus mu cap etc. So that equation you will get the equation for mu cap as okay, and while rearranging you will get mu cap as 1 by n into sigma k is equal to 1 by sorry k is equal to 1 to n xk. Okay, so this will get it. So so if you look into this particular equation, we know that this is nothing but the average, okay, just the arithmetic average of the samples. So okay, so so that means on the left side is actually the optimum value for the mean value or the parameter. So that means it is actually theoretically as well as maybe logically it is correct, okay, because we have found out the optimum value for theta cap, and that is essentially the average value, so which is actually maybe maybe meaningful value that we can actually always okay say about maybe this particular case. So that is actually the maybe the conclusion that we can write it. Okay, so so that means the conclusion is suppose we can follow this that procedure. Okay, that means so suppose we are having okay there are C classes, okay, and assume that they are Gaussian, and d-dimensional feature space, then we can estimate the vector, okay, and perform an optimal classification. So that means we have a maybe in a specific case where we have the variance is actually known and the other one. So that is the mu was actually the only parameter that is unknown. But we could be able to derive an equation for mu, which is actually in accordance with our maybe say belief as well as according to our existing knowledge. So we can say that the steps that we follow, okay, the procedure that we adopted is actually right. Okay. And suppose we are having in the second case, so assume that we are having an unknown mu and covariance matrix also, maybe an arbitrary case. Okay. And there can be, say, suppose we split this into two. So this one is an univariate case and another one is actually multivariate. So assume that is an univariate case with the unknown mu and the unknown. Instead of sigma, capital sigma, that is covariance matrix, we will have only one variance because we are having only one attribute. So that means only one feature. Okay. So the equation will become of this kind. So the parameter vector is theta 1 comma theta 2, and that is the first parameter is say the mean value, and the second one is actually the variance. So there is no covariance because we are having only one feature. So again, the analysis remains the same. Okay, we define the log likelihood function. Okay, x given theta, and you substitute on theta 1 and theta 2. Okay, instead of mu and sigma square, so that you and taking the logarithm, so you get an equation of this kind, which is actually similar to the earlier equation. Earlier we have xk minus, okay, mu into xk minus mu transpose into sigma inverse into xk minus mu. So that means here you have a no, okay, that is covariance matrix. So you will get an equation of this kind. Okay. And then the next step is we have to define what is the gradient of, okay, the L. So that means we have to partially derivative. Okay, actually this is dou actually. Okay, not sigma. So dou by dou theta of this particular function is equal to 0, and similarly dou by dou theta of ln of this one is equal to 0. So that means in order to find out theta 1 and theta 2. So that means now you apply with respect to theta 1. Okay, you can apply again partially derivative. Okay, apply partial derivative on this equation. So here we don't have any theta 1. So we have theta 1 only in this particular term. So that means you can see that, okay, if you apply the partial derivative, you will get an equation of this kind. So because again the same 2 into, okay, rule and cancelling out. Okay, so that is the case. Similarly, when you go for theta 2 is present here as well as here. So then you apply the differentiation, okay, partial derivative rules, so that you will get an equation of this kind. Okay, so I think they are straight. Maybe just apply the rules. There is no complexity involved. Okay, so you'll get an equation of this kind because you will get one term from the first term and the second this term from the second term. Okay, so that is now we have the two equations. Okay, and maybe for the entire training set, okay, it is k is equal to 1 to n the summation. So when it brings to, okay, the our training set, we have a theta cap. Okay, theta cap, theta 1 cap and theta 2 cap. So that means we are actually finding out the best considering the entire training set. Okay, similarly the same equation, okay, changes to, okay, these parameters. So that is a again just the optimum cases. And now again you can actually apply the same rule. Okay, the same steps that we follow, you will get a mu cap like this one. Okay, mu cap is actually theta 1 cap. Okay, similarly this is theta 2 cap. So you will get an equation of this kind and you will get an equation of this kind. So if you look into the first equation, we can say that that's an equation for average value, okay, as we got in the earlier case also, and that is according to our belief and according to our non-knowledge that okay, mean value is something like that, defined like this one. If you look into the variance also, we'll get the similar equation, okay, 1 by n into, okay, k is equal to, okay, so xk minus mu bar. So I think we know about what is actually the equation for variance. So we obtained the same equation by doing this steps. So that means both of them actually according to our maybe understanding, okay, or maybe we can easily accept those cases. Okay, and now When it comes to multivariate cases, we are actually not going to the detailed maybe that equations, but the case is same. The only thing is we have to replace the univariate x and maybe mu with corresponding maybe capital X vector, okay, and maybe say the corresponding vectors. So that's all. Okay, and then we have to replace the variance with the covariance matrix. So as usual. So this is going to be the equations we will be obtaining. Maybe the same equation, but with the replace with the vectors. Okay, so that is actually the so this is a vector and this is also the covariance matrix. So we can actually calculate it. So the same equations. Okay, maybe in the vector form. So that is a case with a multivariate case. Okay, and now there is a last thing. So we have actually defined sigma square like this one. Okay, sigma square. Okay, we have defined a sigma square like this one. Okay, but suppose we are not going again, not into the derivations. Suppose we find out the expected value of this particular maybe term. So that is, this is actually our xi minus x bar is actually maybe the mu value. Okay, the whole square. So that is if you apply the expected value of this one. So because that we know that the expected value is actually the average value. Okay, when we had already seen that concepts. So when you apply the expected value of this one, maybe while expanding this one, okay, and we have actually seen some other intermediate results. What is e of x square? Okay, so expected value of x square we have seen. So so you expand this one, we and then we apply the expectation of on each term, and putting some substitutions, you will be getting an equation of this kind. Okay, so that is n minus 1 by n into sigma square. So this is actually the expected value that you will get from maybe this the definition. Okay, but that is actually okay maybe different from the original sigma square. So because this is actually sigma square is actually the variance. Okay, and we have actually a bias actually coming here in the form of n minus 1 by n. Okay, so that is actually called there is a bias with the variance in this particular maybe say analysis. So for example, suppose we have n is equal to 1. So that means n is equal to 1 means we have the dimension is actually 1. N is equal to 1. So that means we have only a single dimension. Okay. Sorry, not single dimension. We have n is actually the number of samples. Okay, training data. Okay, so in that case, if you apply this particular equation, okay, we have a 1 minus 1 by 1. Okay, so when n is equal to 1, this expected value will become actually say 0. Okay, because this term, okay, n minus 1 by n will become say 0. So that means we will get a expected value of 0, but that is actually not a true. Okay, because even if it is one training data, okay, we have actually a particular value of maybe variance. Okay, so that means there is always a bias. Okay, in this particular form. Okay, maybe due to our analysis. Okay, but this is a very extreme case where n is equal to 1. So usually our data set will not be okay consisting of maybe a single maybe say training data. So we expect that n is going to be large in number. So when n increases, okay, this bias is generally reduced. Okay, so that is actually this particular maybe another point you can just keep in mind. Okay, so and this type of estimator is sometimes called asymptotically unbiased. Okay, so asymptotically say unbiased. Okay, so that is a name. And similarly, suppose you might have seen that what is the equation for maybe this is the variance. Generally, we'll be seeing an equation of 1 by n minus 1 into okay say this particular form of equation. So if we have this kind of maybe say say expression, then usually that n minus 1 okay will be cancelling out with the n minus 1 coming at the numerator, so that you will get the exact value. So that means that is this is a form of unbiased estimation. Okay, so we are not going to the details, but as a part continuation of this discussion, you keep in mind that there is some a variance, but that variance will be decreased when number of samples actually increases. Okay, so this is an unbiased form of distributions. Okay, so anyway, so that again another point you can keep in mind. Okay, so that is a case. Okay, so we have actually our estimator was actually returning this value because 1 by n into that was our estimator. Okay, that we derived, but we know that that can actually result in bias. Okay, but by considering 1 by n minus 1, okay, that is the case, then there is no bias. Okay, so that is a, but it's a very insignificant, maybe when we have a large values of n. So that is one thing that you have to keep in mind. Okay, so that is actually about generally about this maximum likelihood estimation. And so one more is okay, so we have actually a related estimator is also there. A related estimator in the sense that, and related to the maximum likelihood estimation, we have another estimator called the maximum a posteriori estimator. Okay, maximum a posteriori estimator, or generally called an MAP estimator. Okay, so it is very close to the MLE. Okay, but here actually we find the value of theta that maximizes L of theta into P theta. So L of theta we know that is the likelihood function that we have discussed, and P of theta is nothing but the prior probability values of this theta. That means the prior probability value of maybe a mu, okay, theta 1, theta 2, etc., depending upon how many parameters are there. So that means so here the P of theta actually describes the prior probability, because this is also is a posteriori probability, because when we multiply the likelihood with respect to the prior probability, we will get a posteriori probability. Okay, so this is also closely related. The analysis and other things remains the same. It is called a MAP estimator. Okay, so that is the case. But if you look into MAP and MLE, okay, we can say that suppose the P of theta is uniform. Okay, if P of theta is uniform, then that can be ignored, so that you will have only L of theta. So that is going to be is the MLE estimator. Okay, so MAP estimator considers the prior probabilities of the parameter values also. So that is a maybe the relation between them. Okay, and maybe another very closely related estimator of this kind. Okay, so maybe utilizing the same principles. Okay, so that is actually about our maybe I mean the maximum likelihood estimation. So we will stop today with that one, and we will continue in the next class with maybe the Bayesian estimation. Okay, so thank you.